Howdy, everybody. Hope you're having an amazing time wherever you are, whenever you are, and things are going okay for you. Um, Here we are, Advent to Code, day 15. We're still doing some more Intcode programming, and we are going to talk about um, forking and debugging. I don't know why it went out of my mind. It's literally right there on the screen, forking and debugging. And I think the reason why I mentioned we're going to talk about this stuff is because this program lends itself to modifying the int code program so that it can be forked and debugged. And it turns out that there wasn't actually a lot of work to get it to do that, but I thought it would be a good time to talk about it. Before we get started, though, let me just again say thank you. Always appreciate your comments. I'm glad that you are all finding this useful and helpful, and um, I really enjoy interacting with you and looking at your code and stuff like that. Just one quick thing: remember, we're all on a different journey, right? We're all at different places in our programming experiences. So obviously, I apologize if I say things like, "Oh, this is obvious," because it may not be obvious to you. It's obvious to me, but it's only obvious to me because someone else taught me how to do it, or I read online how to do it. Right? Like, it's always a growth and a learning process. So just keep that in mind, and hopefully, what I'm doing and talking to you guys about will be a good learning process for you. You'll get something out of it. And obviously, if you have ways to improve my code or you see things that would go better, I'd love to see pull requests or changes or your thought process or diagrams, designs, anything like that. It's always fun to talk and to learn and to grow. So, with that, I think let's get into it. Let's talk about day 15. And I thought let's talk about the problem first because I think it will lend it will slowly be able to build on why do we need to quote unquote fork and quote unquote debug our code. It might make a little bit more sense. So I won't go over it. Though I won't read the whole thing, but it's called Oxygen System, and the reason why you saw that little repair droid is because essentially what happens is you are your oxygen system breaks, and so you have to find some way to repair your oxygen system, and so you're going to send out this little repair droid to do it. And the int code program that you're going to use, your puzzle input, is going to um, like interact with is going to be the repair droid is the way to think about it. And so the way you interact with it is you send it a movement command, you tell it to go north, south, east, or west, and then it will do its work, and then it will tell you whether it's found the oxygen system that needs to be repaired. Obviously, you can't get there because you need oxygen, but the repair droid does not, right? So that's how you're going to interact with it. Is you're going to give it a movement command, and then it will do its work, and then it will tell you what its status was. Did I hit a wall and not move, or did I move position, or did I move position and find the oxygen system? That's essentially the three outputs you get from the intcode program. So they go through a little process here. You can see slowly you're giving it commands, and it's like slowly finding its way through the system. And eventually it says, oh, it'll spit out the three command and say, oh, here's where the oxygen is. And you can kind of see like here's what the final graph looks like. It says, so you were right here, and the oxygen turns out was right here. And maybe it took you a few steps to try it because you hit some walls, but eventually you did get there, right? And you found the oxygen for part one. So that's the solution. So what should be going through your mind when you look at this thing, right? Is ignore the int code program part of it and just say to yourself, what does this program look like? Well, it looks like a pathfinding program, right? You're going to have some robot, and you're going to try and have it find in the quickest possible way the position, right? What is the fewest number of movement commands to find the from the start to the oxygen system? That should scream pathfinding, right? So, or Dijkstra's, right? So how do we find this? How do we go from the start position to the oxygen system in the fewest number of steps? And I thought it'd be fun just to, I have several videos, right? It's very common in, especially in Advent of Code, but in all kinds of puzzle solvings, to have these pathfinding problems. Maybe use Dijkstra, A star, or some other special implementation, just really depending on it. So how does this work? How does it work really quick? Again, I won't go into super details, but the idea behind Dijkstra is you're guaranteed to find the shortest path from the start to the end, because you're always traversing, you're always prioritizing picking the shortest distance along the path that you've gone so far, right? So just really briefly, if you start at this start node and you can either go here to B or here to A. A costs 7, B costs 2, so you're going to go to B first, right? So you traverse that B node. You go down here, and now the total distance you've traveled is 2, and now you have to ask yourself, where is the fastest path, or where is the shortest path from the places I've gone? Well, you have 7, you have 2 plus 11, which is 13, and then you have 2 plus 20, which is 22, if my math is not right? So you're slowly building up this, like, hey, here's all the places I can go. Which one has the shortest total distance to travel so far? And even though we went here first, going here or here are now much larger than going here. So we actually then choose this to go here, and we know that to get here, the shortest distance is 7. And we wouldn't go this way because it's now 22, right? Um, so now we have a 7. Now we have a potential position right here and a potential position right here. And again, we just calculate all the edges. This would be 22. This would be 13 to get us here. And this would be 11 to get us here, right? Well, 11 is shorter than these two. So we take this path and we go down this, and it's 11. And oh, we've reached the end. We know we're done, right? We know we've reached the end, that we've found the shortest path. And again, I won't go into the details, but that's at a very high level how Dijkstra's works. You're guaranteed to find the shortest path if you can, if you continually, all of the places that, all of like the frontier of the places that you haven't, that you could potentially visit from where you've gone, if you always pick like the shortest among them. And so the way you usually implement it is some kind of priority queue that keeps these sorted, like a heap, for example, where say, oh, I'm always going to keep the shortest path on top, so I can just pick the shortest path and continue going on it. Okay, so that's a great solution to the problem. The question, though, then is, well, how do I apply this to my Intcode program? Notice in the program, or no, in the description, it kind of tells you, as like, if you think about the way it would work, is you run this Intcode program, you give it a movement command, and then it's moved there, and there's no real way for you to like go step back and say, oh, let's go back or track it. I mean, you potentially could, is you could say, okay, I'm gonna go this direction, see where it is, and then I'm gonna go back, and now I have multiple directions. But that in my mind, it adds some complexity to the program, right? What would be more useful is at any time, at any position where the robot is, could I just kind of like fork the Intcode program? And by that, I mean, could I create a copy of it and then simulate it moving north, south, east, and west, right? Because if I could do that, then at each position, I can easily kind of like fork, or make a copy of the program and just have it go in these different directions. And the reason why I keep using the word fork, if you're not familiar with it, is because that is actually the name of a system call in Linux, right? So if you're familiar at all with Linux, you may have heard of this before, but I thought it'd just be fun to look at this. If you're writing a program and you want to like make a copy of your process, there is a way to do this. And this is the Linux way. There's ways to do it in Windows, Mac OS, FreeBit. All of them have their own way. Many of them call it fork, but they're akin to spawning a duplicate process is the way to think about it. And so just really quickly, what does it say? It creates a new process by duplicating the calling process. Um, right? So think about what you're doing. You're duplicating your program. And that's kind of what we want to do here with our thing, right? Is we want to take this program that's running, it has its own set of memory, and it's updating its code and doing that stuff based on movement commands you send it. But at any point in time, we want to make a copy of it. In fact, we want to make 4 copies of it and try each of the directions and see how that alters the program, and then determine if any of those are worth like keeping around to continue traversing, right? Obviously, if we hit a wall, that's not interesting. Or especially for Dijkstra, we don't want to go back to some place we've seen before. So if we hit some position we've seen before, we only want to keep like the one that got us there the fastest, right? So you kind of do this like filtering of all these things. But again, the idea is we want to do this fork. And notice it tells you a little bit about this fork command. It says it's an exact duplicate of the parent process, except for these following points. And most of them are not really applicable to us in this thing. But it does have things along this line where it says the child, like the forked process, the child does not inherit outstanding asynchronous IO operations from its parents. And this is not exactly how our Intcode program works. But if you think about it, especially in Rust, if you're implementing your Intcode program in Rust, when we're creating channels, if you remember when we were creating those, they were called multi-producer single consumers. That means that there's only one consumer of the receiving end of that channel, meaning you can only have one of them. That is to say, it does not implement clone in Rust, right? So you can't make a copy of that receiver. And that's a little bit along these lines, right? So if the parent was doing any of these asynchronous processes, those don't get inherited from its parent. And there's a reason why they don't do this in the kernel, right? Is you don't want both of those processes to be having asynchronous reads and writes, kind of like stealing from each other, if that makes sense. It is kind of like a high level way to think about it. Again, I'm sure as you look through this, you may say to yourself, "Oh, but there's these gotchas." It's not a true one-to-one mapping, but I do want to mention fork because, again, we're talking about creating this Intcode program, and it's really cool to me how as you're going through the days, you can find corollaries to real-world scenarios, right? And this is one of them, right? You will fork in real life. You actually probably do it and may not know about it. I guess you may not fork, you may create threads, right? But these things are real things that you do in life that could quite possibly happen. This is fork, I should say, is like the old man's thread creation. This is what we used to do. If you wanted to spawn a new child process to do some work that on its own, you would use the fork command, right? Now we largely use threads. Fork is very heavy, or maybe the better way to say it, it's more closely tied to the operating system. Meaning, like it said, what fork does, at least in this Linux thing, is it literally takes like the memory location where all your code is running, makes a copy of it, puts it somewhere else, and then starts another process running in that place, right? And that's actually exactly what we want to do here, right? You think about like what we need here in each of these states. Like when we are here in step B, right? We have 2 potential paths we could take. We could go here and we could go here, right? The interesting thing is we actually don't know much about like the cost, right? These costs are kind of like canned, but we don't have an act. When you start, you don't know what the map's going to look like, right? So you're kind of building that frontier as you go. But that being said, when you're here at position B, what you really want to do is you want to make a fork of B right here and a fork of B right here. And then you want to say, hey, move this direction and move this direction. And you also will say, move this direction and, move this direction. But the droid will, the process, right, will say, oh, you don't want to go back. That takes you back to the start. And you can't go here because that's a wall, for example, right? Um, but there is these two right here. You definitely want to, like, quote unquote fork the process, right? So when you think about what state you're tracking here, is the state for the node, like this. What are we interested in? Well, we're obviously interested in, like, where are we? I apologize for my handwriting. And then we're also interested in is what is the process state. And possibly, like, have we found the O2 system, right? So those are kind of like the three things we're interested in right here, right? And the cool thing about it is, if we have this information, like if we know we're right here, we can create all of our neighbors, right? And that's part of the thing about Dijkstra's, is how do you, like, find your neighbors? What did I say? Cool. It's an important part of Dijkstra's process. You need to know how to find your neighbors. It's really easy when you're in a graph situation like this, because the neighbors are literally just the edges, right? So your graph structure will tell you, hey, here's all the edges, or here's all the neighbors to this specific node. For us, we don't know that, but we can calculate our neighbors with this information, right? So at any given point, when we're here in node B, we know where we're at. We're at node B, right? And we know what our process state is it whatever the memory was, that where we were here, and we said move this direction, right? So we know what this state is right here, right? And all we can do then is just we literally fork that state with a new process, right? We say, hey, take the memory I have right now, create a new process based on that memory, do the fork, quote unquote fork. I actually don't think I call it fork in the code, but maybe I should have, so it'd make more sense. Um, with all this talking that I've been doing. But do the fork and then just try and move at each location, right? And try and move each direction, I should say. And it'll come back and say, oh, you can't do this way. This one does take you back to here. Dijkstra's will ignore it because, oh, I've already visited that node. But then it will say, oh, you can go this way and you can go this way. And now I'll give you your two new neighbors. And then each of these neighbors will have a process state that are different from them, right? And by doing that, you've now created, like, your neighbors for the Dijkstra's algorithm. If this isn't making sense, I apologize. It might make more sense when we get to the code. But again, to highlight, one of the important things you need if you're solving Dijkstra's algorithm is, what are my neighbors? And because we aren't using a traditional graph, we need to, like, figure out what those neighbors are. Kind of on the fly is the way to think about it. And the way that you do that is you like, quote unquote fork your Intcode program and tell it to go in all the different directions. And now you know what all of your neighbors are. And you can determine which ones are valid and which ones you'll continue down the path with, right? Okay, but that does bring up another interesting thing about this, and where we're going to move next, which is breakpoints, right? So if you think about how how your Intcode program is running, particularly for this day, right? You're going to send it a movement command, one of these, and then you're going to wait for it to do its movement operation, and then it's going to report its status, which is one of these, and then you're going to make a decision on that, right? If you think about what's happening here, though, like, so imagine this is your input and you give it, like, a 2, for example, and it spits back 1. meaning, oh yeah, I moved to a new location and but there was nothing there. Um, at that point, we kind of want to pause processing is the way to think about it. And I will just say, after I kind of did through this, well, I immediately thought, oh, it would be cool to implement breakpoints so we could kind of highlight debugging. Because what you're kind of telling, what you're kind of wanting when you fork, what you kind of want to do is tell the process to like pause after you output this one, pause where you are, don't do any more processing because I don't want the state to like to get messed up or whatever. And then I want to like extract this state so that I can get the um, state for the node right here, right? Get the node state where we need that process state. This line right here is essentially saying I want this little blue thing in here to be able to process it, right? And why do I want that is because, again, remember, we're doing a multi-producer single consumer. I can't copy this part of the process, right? I didn't switch over. I can't make a clone of this part, but I can 100% make a clone of this part, right? And so the idea is, well, if I can extract that, I can make another copy of it and say, okay, this output of one, but what if I do, what if I make a whole bunch of copies of this and um, each of these are like a derivative of this state, right? So I pull it out, I do the state, and I pull it out, or I tell it to move this direction, and it gives me this state, and then I tell it to move this direction, and it gives me this state. But again, the way that I've done that is, maybe I'm not showing it very well here, is you have some initial process that has its state, and you want to make clones. So it probably actually would make more sense if it was looking like this, right? Um, but while all this is happening, I'm sorry, I'm spending more time fidgeting than I am actually describing it, right? So the idea is this app state, I want to pause the process, and then I want to create a new process in each of these things and tell each of them to go a different direction, right? So this one I'll say go north, this one I'll say go west or whatever. I don't remember the exact numbers. And then they'll each output different things, right? This one will output a 1 or a 0, and this one will output a 1. And then I will do that, so on and so forth. But at the moment that I do this right here, I want to pause the process, right? I want to say, oh, hold on, stop right here. Don't do any other work so I can extract the state and move it through. And again, I should say you technically don't need to do this pause. There's ways to do it where you say, okay, I'm going to step until I get to this thing that I'm interested in, and then I can stop. But I thought it would be fun to show you how to do the debugging. And it goes in. Why do I want to show this? Besides the fork thing, also the debugging, these are things that you can do in real life, right? You've probably spun up a debugger before, and I'll spin one up right now so you can see it. But the idea behind the debugger is there's points in time where you want to like, oh, I want to pause. They call them breakpoints. So I can inspect what's going on in my program and see what might be going wrong with it, or make changes on the fly, right? So let's do it. I'm opening VS Code. It's not my favorite tool, but a lot of you people use it, and I think the debugger actually is a great visualization of what's looking on, and that's why I'm using it. I think if I showed you the debugger in NeoVim, it might confuse a little bit what's going on. It doesn't look much different, but I think having the mouse and this visualization may help you, so that's why I'm doing it. So I have this super simple program in Python. If you're not familiar with Python, don't really worry about it. We're implementing a factorial function, and basically what we're doing is the simplest way of solving a factorial is you say, well, if you ask me for factorial 0, I give you 1. Otherwise, I give you factorial of the number and the number minus 1. And you can just do that recursively through the thing, right? But if I want to debug this, what I can do is kind of set a breakpoint here. Like, for example, let's set a breakpoint here. So now what I'm telling by doing this breakpoint is, hey, when you debug this program, I want you to stop right here, right? I want you to stop processing at this point in time. And so let's just try that, right? So we'll go here and we will say run Python debugger, debug Python file. So we're now debugging it. You notice it popped up this debugger. I'll move this over here so you can see it. It kind of gives us these instructions that tell us whether we can step or not step, or how we want to continue processing. But you can see that it's actually broke. It stopped processing at that breakpoint. You can see here's where it's at. This little yellow arrow is indicating where it's at. And on this left-hand side, you can see my call stack, right? It called main, and then it called my factorial function right here, and then the local variable was 5, and so now it's down in this position, right? And so now I can step through the process if I want, right? I can say, hey, take the next step, which is something we've done with our Intcode program, and it will go to the next thing. Notice it's changed the local variable. I still have this on the stack where I was at 5 over here, but now I'm at 4 and I can continue doing processing, right? If I hit this continue button, you can think about this as like the run until you hit a breakpoint. Now it will go to here, right? And I can keep doing this. And notice how it's building the stack over here. That's because we're being recursive with our factorial function. But these locals are being updated, right? And it's slowly like it's running this factorial function and breaking when I hit this breakpoint. And this was a very simple example, but if there was a mistake in your code, this is a great way to debug it because you can run through it one line at a time, and you can say to yourself, oh, what's wrong? For example, let's go back. Let's say that we don't have this n-1 here, and we're trying to debug why our factorial function is not working. We can spin up the debugger, right? And you can you say, okay, I've broke here. My n is 5. That's correct because that was the first one. So let's continue, and I continue again, and you're like, oh, n is 5 again. That doesn't make sense. It shouldn't be 5, right? That's just going to keep calling 5s over and over again, and something will break, right? And you're like, oh, that's not right. That's not working. But that may give you an inclination of like, oh, I didn't subtract here, so I can put -1 here. And now it should work the way I expect, right? Like as I continue here, you'll notice that the number decreases over here. Okay, so this is, again, very high level debugging. If you're using VS Code or whatever editor you're using, debugging is a cool way to look at your program and inspect what it's doing, so that you can help figure out what might be going wrong, or debug some code, find out what's going on. But that's the essential part of debugging that I wanted to talk about. I don't want to go deeper into it. If you're interested in more in the details of debugging, like how does it figure out this call stack and stuff, we can talk about that another time. The interesting part for our Intcode program, or particularly for this day, is notice how it can stop processing, right? It can say, hey, run all of this code until this point, right? Well, that's actually exactly what we're interested in when we are doing when we're trying to solve this program, right? Again, think about, I'm going to stop this and close out of it because I think we're done with the VS Code stuff. But that's exactly kind of what we are talking about right here, right? Is we say, hey, I want to be able to take what I want to receive this output, but then I want you to stop. I don't want you to do any more processing, right? If you think what would happen right here, if once you send this instruction, this process is kind of running in its own thread, right? It's immediately going to continue its work, right? And we don't want to do that. We want it to stop at that point. Now, again, it turns out in this program, you're probably okay not to do it, but in any other potential program, you might want to say, hey, stop here. Right after you send this thing, stop, and then I'm going to, fork your state, at least for this problem, and solve the problem. And talking about the debugger, again, that the way to think about it is that's how these debuggers do their processing, right? So you have you have some debugger that kind of wraps around the process, and you send the debugger instructions, right? You say, hey, take another step, and the debugger does the work of just making sure only one step is taken, and then it receives the output and maybe notifies you there, right? And that's how you get like the variable changes and the output changes and things like that. And so we kind of want to implement this debugger in our code, right? So that we can tell the debugger, hey, step until output. I don't know why I drew it like that. I apologize. Um, and then we want to tell it to continue is the next step, right? So we'll say, hey, continue until this point, right? I apologize. That doesn't look very good. But that's essentially what we're telling the debugger. And then it will do that's work. And then it will eventually spit out a thing that says, okay, I'm here. And here, and then it will give you, and then you'll have the state information that you need from here, right? That's essentially what we're trying to implement for this day 15. And again, why does this work? Well, let me go down to this graph right here. As the droid is moving through these things, we want to fork. Again, if it's right here, we want to fork and say, hey, move here, 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 and here. And then for each of those, we want to say, give me your output, but then stop processing. So just run until you give me your output and then stop. And then that way you can go into, and the debugger is what will help us do that, right? It will say, go tell the process to go north, and then stop what you're doing, and then tell me when you're done so I can output that state, right? Okay, that's a lot of talking, but these are kind of like the two things that I think, again, this day helped illustrate in my mind about how the quote unquote real world works, right? It's not uncommon for you to kind of want to fork your process. And it's also not uncommon for you to kind of want to step through your process, right? And we'd already implemented in our 2E a little bit of a debugger, but given this new code, we can actually do breakpoints. And we'll talk about that in a second. But I think at this point, it's probably just a good idea to look at the actual code, right? So, what code changes did we make to implement this? Well, we already have like the step function, and we actually already have the ability to clone our state, right? At any moment in time, we can say, hey, what is the current state? I think I showed that in my 2E stuff, but we can actually just, the state and the actual process are two objects. And even though the process like encapsulates the state, at any moment you can say, hey, give me the current state, and just spit out the state. So we already know how to like duplicate it, like fork it, maybe is the way to say it. We do need to do something like be able to create the fork. And so one way we do that is with this with state, right? You notice my original new, like create a new process, is you gave it the program and its input IO devices, right? And then it started its processing. Well, now I have a with state function that says, oh, just use this existing state to start up the program, to initiate program running. And this is, again, I named it wrong, but you could think about this as like the quote unquote fork. You could potentially do this with another thing, right? It's like, hey, fork this process where you create new inputs and outputs, but you use the identical state. And that's what this with state function does. But then the other thing we need is the breakpoint code, right? And that's this run and tell function I created. We had a run function which just kind of goes through until it stops. Again, we don't want to do that because we want to like break at some point in time. Um, and I should say, maybe I haven't said this before, again, you could potentially call this run function and then just clone the state after you get the output. But there is these like race conditions I was worried about. And that's why I think run and tell is better, because you can now say, hey, run until some condition is met. And that I kind of did these in these orders because the run will just run forever, right? It's just going to run until it's halted. And the step function is like even lower level than our run until, where it says, hey, just take the next step. And again, you could potentially use this step function as the solution, right? Is basically you just step until you do an output and stop. And you'll actually see that's what I use kind of up here, but or similar to up here. But the run until is kind of like that continue statement that we talked about when we were doing the debugger, right? It says, hey, I want you to run until some condition is met. And here's what that is. And this is just Rusty's for give me some function that takes the state and instruction and tell me whether or not I should keep processing, right? And so I'm just going to take, and I do that in just in a big while loop, right? So here's my while loop until the program's quit. I'm going to get the next instruction. Then I'm going to ask, I'm going to call my conditional statement here and say, hey, should I break at this point? And if I do, I break out of this loop. Otherwise, I actually evaluate the instruction. And that allows me to like step through it over and over again. Maybe it will make sense too. So I've created, I updated the TUI to do this. So if you look right now, there's no real breakpoints. But if I hit B, I can create a breakpoint, and I'm going to do it on, and let's do it on memory. And I want to break at, let's say, 72, right? 72. So I want to break when the instruction pointer gets to 72, right? And so now if I hit continue, you'll see it zips until it gets to 72, right? And you can think about this as like the, hey, I want you, you set the breakpoint in VS Code, and then you want it to stop at this point. But you can see what happened is it essentially said, hey, run until you get to that point. And that, the TUI, there obviously I had to implement the TUI to show kind of like the stuff and how to set breakpoints and create them. But the TUI essentially calls run until, and it's tracking those breakpoints that you've set, and the function that it gives this run until will check that instruction pointer, right? It says, hey, am I at this instruction pointer? And if I am, I want to break, right? So just if I do that one more time, I'll quit out and I'll start again. I can, right now I have no breakpoints, but if I set a breakpoint for memory location 72, and I look at my, you can now see there's a breakpoint in our Intcode, in our debugger that says, hey, I want you to stop at 72, right? And now if I hit, obviously I can keep stepping, but if I want to just zip to the next point where I hit that thing, I can hit there, continue, and it does all the processing until it gets to that point, right? And again, I've spent a lot of time talking about this, but what does that help us do? We now have all the tools we need to use Dijkstra's algorithm to create those neighbors, right? That's where this all started. Is we've been on this 40-minute journey, but we read the problem and we knew the solution fit a pathfinding algorithm. It was just a question of how do we determine what state each of these nodes are, and how do we determine what its neighbors are, right? Where can each of them go next? Those are like the primary things you need to solve a pathfinding problem. Is where's the next space, and possibly how long does it take me to get there, or where are my neighbor nodes and how long does it take me to get to them, and then how do I track that state that is necessary to like get from each of those points, right? So we do that with breakpoints and forks. And so let's just, given all this, we've talked about it for a while, let's actually look at the code, right? We have this run until function. We have this with state function that we add. So let's look at the code and see how we process this. And I want to start with this IO loop thing. Think about what we have to do at each point in time when we want to determine what what the neighbors are of our current position, right? I'm sorry, this got a little messy, but the idea is if we're right here, how do we determine that we can go here and here, right? Well, you actually just need to run the process, right? So you create a copy of the process at this point. You tell it to go this direction. You create a copy and tell it to go this direction. You create a copy, tell it to go this direction. You create a copy, tell it to go this direction, right? So this IO loop you can think about is that tell it to go this direction, right? So given a current state in the direction you want me to move, I'm going to create a process and go through that loop, go through that one iteration, right? So I set up my channels, I send my movement command, right? That's sending it to the input of the program. Then I create my process. Notice now I'm using the process with state function. I have some existing state. I don't want to create a copy of my original program. I want to create a copy of the process at this point in time, right? Right here where I'm at. And then I want to run until some condition exists. And for this one, it happens to be at the output, right? So at the point that my program is going to output the instruction or the what happened when it executed the command I gave it, I want to break at that point, right? So that's what this does. Sorry if it looks a little funny, but I'm using a closure here to say, hey, the breakpoint is given a state and instruction. I want to break when the instruction matches an output, and this is just kind of like Rust shorthand for that closure. But I call run until, and I pass it this breakpoint function. And if you remember, the run until is just going to step and do all the processing until it hits that point in time, right? So now I've stopped at that point. I haven't actually executed that function, right? If you remember when we were breaking, you break at that line, but you haven't actually executed that line. So I just step one more time to do the actual output, right? So now it's sent a message, and then I can receive that message, and that will be its response, right? So this IO loop you can think about as like one cycle of send an input, do the processing until the point of output, and then execute that output command, step once, and then read the results of that output. And this is not unlike how your debugger would work, right? These breakpoints are more complex, and I won't show it, but you can look at the TUI code where I keep a list of breakpoints, and then the function is just iterating over those breakpoints to see if any of them are met, and it calls run until for those, right? But this is essentially how the debugger works. It starts up your program. I think I had this in one of the diagrams, right? It like starts up your program with your inputs and your outputs, and it does the processing that you tell it to do until it hits some breakpoint that you want it to break on. And then you can do the stepping, you can do the continue, right? In our case, it's very programmatic. We know exactly what we want to do, but this is like at a high level of how that would work, right? Okay, so now that we've done that, now that we kind of have this little function that will do each of those, well, what does our neighbor's function look like? It's up here. It is actually really easy, right? For all the directions, we're going to call that IO loop, and then we're just going to check and see what the result of that state is, right? Obviously, if we hit a wall, we're not interested in that neighbor, but if we found it, we want to mark the option as true, otherwise we want to mark it as false, and then we want to add that neighbor to our state, right? So this is like this thing right here is calling that loop on all four of those things, right? It's saying, hey, try here, then try here, then try here, then try here, and then give me keep track of all the valid neighbors and return that neighbor, okay? If you've been following along with the async stuff, this code may be interesting to you right here. This is saying, so we could have technically written our own Dijkstra, but I ended up using the pathfinding package where I can just call Dijkstra on it. And it is not asynchronous, right? So it doesn't, at least as far as I know, doesn't have any way to do an async function. But all of our code is asynchronous, right? So we can use this special, and I even I didn't like shorten it so that you could see this is part of a futures package. Basically, what you're saying is, hey, I want you to run some asynchronous code until it's done, right? So I want you to, until this IO loop await returns. I don't want, I want to block on that, right? This is just a kind of a fancy way of doing that, or not fancy. This is I mean, it is fancy, but it is cool because what it allows us to do is say, hey, I have some asynchronous code, but I'm in a synchronous system right now. So run that asynchronous code until it gets the result that you want. And that's essentially what this does, right? It's a cool little bridge. You'll actually see this a lot in, so libraries, for example. I don't know if what's one I've talked to? Oh, like MongoDB, you can make asynchronous calls to the database. Like you can say, "Hey, get me this result," and then it will kind of, it will put that thread in the background until the results are ready to come back. Um, they will often have asynchronous and synchronous solutions in their package. And essentially, if you like, for example, a query, the asynchronous one would just be the asynchronous function, and the synchronous version would literally just be a block on, meaning it runs asynchronously, but it just calls block so that it's synchronous. That's not always the case, I should say, because there's obviously adding asynchronicity to your program brings a runtime with it, and maybe you don't always want that runtime, but you'll often see that happen with packages. So again, I can't say specifically that Mongo does that, but this was all a deep, I'm sorry I went down this path, but the idea is this block on is actually kind of useful when you're trying to bridge asynchronous code to synchronous code, and that's exactly what we want to do here, right? But again, at a high level, what is our neighbors function? We're literally just saying, try to go every direction, fork our program for each of those directions, and ask it to go that direction and see what its state is at, or see what output it gives at that point. And what happens in there is we create that fork, we run until our breakpoint, then we get our output, or we step for our output command, we receive our output. And now we have a functioning, working neighbors uh, command or function that we can use in our Dijkstra. So what does that look like? Ignore this for part 2 for right now, but for part 1, obviously we need to have some state. I think I talked about this before in the thing, but I haven't actually shown it to you, right? We want some node in our quote unquote graph that we're traversing. And what is that? Well, we want our point. Where are we in space in our graph? What is the state of the Intcode program that will allow us to help find our neighbors? And then we want to know whether or not we have oxygen, right? So we'll create our start node, which is at 0.00. The point doesn't really matter. You actually only need the point for part 2, but we do need our state. And what is the state? Well, it's the input. The start state is the initial input, and obviously we haven't found the oxygen. This is kind of a helper function primarily for part 2, but the idea is we want to get our neighbors, and then we want to tell the pathfinding package what the distance is. The distance is always 1 in our case, and so that's what this is. And this is for part 2. If you weren't doing part 2 and you're just doing part 1, you could potentially just use this neighbors function and just augment it with the distance. It wouldn't be too hard to do. But again, so I have my start state, I have my neighbors function, and normally you would have an end state. So if you've gotten to, or if you've watched the previous videos, the reason why Dijkstra's is so fast is you don't have to traverse the entire graph. It will find the fastest point to the end relatively quickly, and it won't visit all the nodes to get there. It may have to, but it won't necessarily. For part 2, and I don't actually have. Oh, so what? Why do you? How does that? What do you need also to know at that point is how do you know if you've reached the end? And that would be where the oxygen was true. You notice I don't actually call that here, and I highlight this in the comments. Normally, you could just run Dijkstra and say you're done when you've hit something where the oxygen state is true, or the state of the oxygen is true. But for part 2, you're going to do a breadth first search of the entire graph. And so I actually run Dijkstra's all here, right here. And what is that saying is, instead of just finding the end node, traverse the entire graph and return the distances to every point in the graph from your start node. And so this dists actually will tell you exactly how far you are to every single point in the graph. And that's helpful for part 2 because you end up having to do this breadth first search. And so you actually want to know all of the nodes. If I just ran Dijkstra, I wouldn't know all of the nodes. I would only know the nodes that I had visited. And that's why I call Dijkstra's all here. But again, if you're just thinking about part 1, just gloss over that part for now. I've created a neighbors function that does the work we talked about earlier. I have a start point, and then I can just call Dijkstra's, and it will find it for me, right? And it finds it relatively fast. So what do I have to do because I use Dijkstra's all? Well, I just have to find the node that had oxygen in it, and that will contain the distance that it took to get there, and that's my solution to part 1. So if I... what are we on, day 15? You can see it spits it out, and it does it really quick, right? Like, I haven't timed any of this stuff, but... oh, do I not have time set up? I think I'm spending too much time worrying about this. I mean, you know, the whole... I do part 1 and part 2 in about 25 milliseconds, right? Or that was the mean, about somewhere on the order of 25, right? But again, this is all to say it runs pretty fast, right? The graph isn't huge, but again, because I can use Dijkstra and just do that processing, like just what is the next step, I can get to a solution really quick. Okay. Let's move on to part 2, and then we'll do... that's most of the day. Part 2 actually isn't much tougher, but we'll look at it. So what happens to part 2 is it says, okay, well, now that you've found the oxygen, the repair droid repairs it. So thanks, repair droid, for saving my life. And then it wants you to figure out how long will it take for the oxygen to get to the rest of the ship, the rest of the system, all of the thing, right? And it says, like, at any moment in time, it takes 1 minute for oxygen to spread from its any O to all of its neighbors, right? So you can think about, you're kind of doing this flood fill of the thing. Slowly, all of the oxygen is moving to each of the things out and out and out. And it shows you how that works. But then the question it asks you is, how long does it take such that the whole graph is filled with or the whole graph is filled, right? The whole spaceship is filled with oxygen. And in this case, it takes 4 minutes because you start here, and then at the first minute, it fills these two. The second minute, it fills these two. The third minute, it fills these two. And then the fourth minute, it fills that one. And so now you're done. Well, we've already, again, like I said, the hard part was implementing Dijkstra's, right? And so I call Dijkstra's all because that will now give us all the nodes. We now know where all the nodes are in the graph from the robot repair droid. So I really just need to track what are the points in the grid, and is there oxygen? Where was the oxygen in the grid? And so this is what I'm tracking for part 2. And this is why I have this neighbors closure right here, is because once I call neighbors, I can add those into my grid, and I can track when I found the oxygen, where it's at. So this neighbor Dijkstra's is going to call this function for me, and it will slowly find all the nodes on the graph. And I can just say, hey, for each of those neighbors, before I tell Dijkstra what the neighbors are, I just want to add that to my grid and check where the oxygen is. So once I've done that, now it's just a breadth first search. And I won't go into the details too much of how this works, but the idea is, I mean, Dijkstra's is kind of a breadth first search, but it often stops when you found it, right? In my case, I'm going to do a full breadth first search. I'm going to visit all the nodes. And so how do I do that? I just have a vec deck where I start at the oxygen position, and then I slowly work my way through literally every single node, right? So yeah, spread throughout the node, through all the nodes, and just track the one that had the farthest distance, right? This will be somewhere near the end of the thing, but it's not necessarily the last node. And so you just kind of track like, hey, what's the farthest I've had to travel from the oxygen system, and that will get you the answer to part 2. So again, this wasn't really related. I didn't do a lot of commenting. I think I've done BFS algorithms before. If I haven't and you're interested, I'm happy to talk about them. But this really wasn't the part of it. But this will get you the solution to part 2, right? And that's the reason why I use Dijkstra all here. Again, if you're only interested in the one, you can just use Dijkstra. Okay, what a long journey this has been, right? But I just want to highlight some cool things that I think about, again, about this Intcode programming. It's really fun to do this stuff, right? You're given a program, and you're trying to find some way to solve it. And the way that I felt was the most beneficial to helping us understand real world programming is through forking and breakpoints, because those are real things that you will really be doing in your programming in real life, right? Maybe not forking per se, but you will be using threads, and threads are, maybe in the same like category of forking or whatever. It won't be uncommon for you to use these tools. And so working through the problem and understanding how it works at like a high level, I think is really cool, right? I spent a lot of time implementing the debugger and the breakpoints in the TUI, and it really helped me understand how, you kind of take it for granted when you say, hey, spin up my debugger. What is it doing on the end, right? And again, it's really nice to have. When I grew up, back in my day, we used like GDB, for example, and it was very like not visual. It was in the terminal. You could still get the same information you needed, but it was much more harder to see what's going on and where you're at and what's happening and stuff like that. And that stuff has grown over time, right? Now in all of your editors, you can find a debugger that will show you how to do that. But understanding how the debugger works, I think, is actually really cool, right? And so if you spend some time trying to solve this problem in the, hey, can I breakpoint, that will help you find it. I should say for this problem and other problems, another potential solution, which we may talk about, is like hacking the Intcode program. Like, can you quote unquote disassemble the Intcode program and understand how it works? And you might actually find in memory what the graph looks like, right? So it's quite I haven't actually looked at it, but it's quite possible that there is a region of memory in the Intcode program that describes the graph, and then it's just storing where the robot is, and how it is, and then based on the input instructions you give it, determines how what it's going to spit out as its output, right? So if you wanted to be like Hacker Man or whatever, you could potentially disassemble the Intcode program and get an actual picture of the graph, and then you can just run Dijkstra's on that picture or on that graph. And it's something that came to my mind, so we may actually do that. So you can, and that will be another video, is, hey, can we disassemble an Intcode program so that we can actually view it, see what it's happening, and understand how it works? Anyway, that's a potential other solution. But again, I kind of wanted to stick to the, hey, here's some cool things and here's how they correlate to real world programming. And for today, forking and debugging seemed like really good candidates for that. And I think it led to a good solution, right? And again, like how do you get there? Well, you look at the problem and you say to yourself, "Oh, this is a pathfinding problem. It's a Dijkstra problem. So what do I need to know? I need to know where's my starting node, how do I find my neighbors, and how do I know when I'm done?" Right? Those are kind of the three high-level things you need to do when you're doing an Intcode program. And or sorry, when you're doing Dijkstra's algorithm. And that led you just keep working your way down the path of, okay, well, how do I find my neighbors? Obviously, I need some ability to like pause the process. And then once I paused it, I need some ability to like fork the process. Um, and that's where debugging and forking came in for me, right? Um, and that's how I got to the problem. So, okay, this has been a long one. It's been an hour, but I think we talked about some cool stuff. And I'm interested in how you solved it too. Did you do it another way? Did you find some other solution? Were you Hacker Man? Those things would be cool to see too, right? And I don't have a problem with solving this any of those ways, right? I think if I were initially doing this thing and it wasn't for like this series of videos, I may have tried the Hackerman approach is like, can I just find where it is in the Intcode program, where the graph is? Because if I can find where the graph is, I can then easily do Dijkstra's on it, right? And that would get me there. So that's all again to say. I'm interested in your solutions. So let me know. Please send them to me. I'd love to see them, and we can talk about them more. But I've posted all this code, and I'll send you links to my code and the solution or the problem, and some of the links that I showed you in the code and stuff like that. So hopefully this video was helpful for you, and you've learned something. And again, please let me know if there's anything I can do to improve my code, or look at it. But with that, I will say thank you and have an amazing day, night, evening. I don't know, wherever you are. Maybe you're in a spaceship and it's always day. And if that's the case, you are both a lucky person and probably a future person. But regardless, I hope you have an amazing day as well. And with that, we'll talk to you later.